Hello friends, welcome to the first part of a motor controller design video series. Today we'll be doing a brief introduction or review to AC motors. This section is going to be split into two videos. We'll be covering the basics of three-phase AC motors, what they are, how they work, and what kind of different AC motors exist. Finally, we'll establish why we need a motor controller in the first place and outline some of the basic functionality we need the controller to do. This last part will help us transition into the next few weeks. We're actually going to start talking about some of the hardware and software going on. So fundamentally, all a motor is it's a device that converts electrical energy to mechanical energy. As the name implies, AC motors require AC power in order to generate mechanical energy. Typically, we generate rotational energy, but linear motors do exist. Rotary motors can be found in just about everything. RC planes, electric vehicles, laundry machines, power tools, mills, lathes, you name it. Linear motors do exist too, but they're usually found in factory settings or in maglev trains. So how do these motors work? And the short answer is with magnets. If you've ever played with magnets before, then you know that opposite poles attract and like poles repel. This is the fundamental phenomenon that also allows motors to function. So let's take a look at this simple example. I do want to make a quick note. For the purpose of explanation, I'm only showing one half of the magnet here and here. In reality, a magnet can't exist like this. It can't exist as a monopole. If there's a north pole, there has to be a south pole. However, for the sake of explanation, we're just going to ignore that part because we only really care about the pole that's facing inwards. Okay, so in this example, we have a bar magnet that's allowed to freely rotate about its center. We'll call this the rotor, and surrounding it, we have some magnets, which we'll call the stator. The stator is fixed in place unless we put energy into the system to allow it to move. So in this configuration, what we expect to happen is that the north pole of this rotor is going to rotate towards the south pole of the stator, and the south pole is going to rotate until it's hitting the north pole. Okay, so now let's say we put energy into our system, so we cause the stator to spin 90 degrees. We're going to hold the rotor in place so it can't move, but the moment that we let it go, we expect the exact same thing to happen. North pole goes to south pole, and south pole goes to north pole. And we can effectively keep doing that. If we keep spinning the stator around and around, the rotor is going to keep spinning around to chase it as well. However, there's a bit of an issue with our current setup. Right now, we have to put mechanical energy into our system to cause our stator to move because these are permanent magnets. This doesn't really do anything for us. We're just taking mechanical energy and converting it to mechanical energy. We want to put electrical energy in our system to actually do some useful work. So how do we do this? And the answer is with electromagnets. As you might have learned in high school or undergrad, if you have a coil of wire and you run some current through it, you'll generate a magnetic field. Additionally, if you run the current in the opposite direction or you wind the coils the other way, you're going to generate a magnetic field pointing in the other direction. Furthermore, we can also place something like a ferromagnet, iron, or something along those lines to make the magnetic field even bigger. So let's go ahead and do just that. Let's take two pieces of iron and wrap some wire around it. We can actually use the exact same piece of wire. We just need to coil the windings the other way for one of the cores. We'll call this A and A prime respectively, since they're just equal and opposite. While we're at it, we're also going to make two other pairs of coils, B, B prime, and C, C prime. We're going to see why we need these later. So now we know that we can put some energy into the system to create a rotating magnetic field. The question is, what exactly does this electrical energy look like? And it turns out the answer is a sine wave. So applying sine waves to our coils will generate the rotating magnetic field that we're looking for. To see this more clearly, let's take a look at this example. So let's say we want our rotor to face in this orientation, where the south pole is facing towards A and the north pole is facing towards A prime. In order to do that, we're going to have to generate a north pole at our A prime. What this is going to correspond to on our sine wave is +1, which is 90 degrees. And if we take the exact opposite example, let's say we want to generate a south pole at our A, we just have to travel 180 degrees either mechanically or electrically on the sine wave, and we'll see that we need to apply -1 to our A. And doing just that will generate a south pole at our A and a north pole at our A prime, which will get the rotor orientation that we're looking for. And at this point, you might have realized that the initial example of two magnets isn't entirely true. Rather, what we're actually doing is we're creating a gradient. So as we travel along from our north pole to our south pole, the magnetic fields will get weaker and weaker, but it's still going to be a north pole. So we'll have a strong north pole here, and it'll continue to get weaker until we get to the 90-degree mark, at which point there's going to be no field. And then as we keep going, we're going to start with a weak south pole and it'll keep getting stronger until we get 180 degrees from our north, where we get our biggest south pole. And at this point, you might have realized I lied about something else too. Our A and our A prime coils can't actually generate a north pole facing a certain direction. They actually have no ability to generate a field apart from the location they're sitting in. So what's actually happening is that they're generating a magnetic field that represents the part of the gradient that they're sitting along. So let's take a look at this example. Let's say we want our north pole to face 45 degrees from our A, and our south pole to face 45 degrees from our A prime. So if we move along our sine wave, we see that we're just applying a positive signal to our A and our negative to our A prime. It just so happens that it's weaker than our max of 1. And at this point, you might have realized there's a limitation with this setup. And if it's not entirely clear to you yet, let's take a look at a different example. So let's take a look at a rotor pointing in this configuration where we have a north pole facing towards our A and a south pole facing towards our A prime. And let's say that we want to generate a magnetic field such that the rotor rotates 90 degrees, so that the north pole faces towards the south and the south pole faces towards the stator's north. If we look at our sine wave, we actually have to apply no signal to our A and our A prime. This is kind of an issue, and in theory, there's actually no way to rotate the magnet in this orientation. Since we can only generate north and south poles of varying magnitudes, this can't do anything, because they'll always be parallel to our magnet. This is kind of like trying to close a door by pushing really hard towards the hinge. If there's no torque on the door, there's absolutely no way to move the door. And turns out these are both states of equilibrium. While this first configuration might be obvious, the second one might not be, because you might be thinking that this rotor actually wants to rotate 180 degrees to get so that the north pole is facing the other way. And like I said before, there's no way for the rotor to actually turn here because there's no perpendicular force. So this happens to be an unstable state of equilibrium. We can kind of think of this as a ball sitting on top of the hill. It's not going to move from its position, but the moment that it moves just a little, it's going to roll all the way down the hill, versus our previous state of equilibrium, where it was like a ball sitting at the bottom of the ditch. Even if you moved it a little, it's just going to come swinging back around to its original position. So how do we fix this issue? Well, you're actually going to have to tune in next week to see how we fix this. That's about it for today. Thanks for tuning in. I'll see you guys next week.